Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Good afternoon, everyone, and thank you for attending today's webinar on advanced spray drying technology for the DoD. I am Travis Neen. I am one of the research analysts at DSIAC, and I will be emceeing today for Steve Rowley. And to give a quick overview of how this is going to work today, after the quick intro, I will be handing it over to Steve for the presentation, and at the end there will be about 15 minutes for a Q&A session. If you have any technical difficulties, you can try dialing in and following along with the slides, which can be found on our website, which I put into the chat. And if you have any questions during the presentation, you can submit those on the question button at the top of your screen, and we will go over those at the end of the presentation. We will also be recording this presentation and it will be made available afterwards. And so without any further ado, I would like to introduce Steve Rowley and hand the rest of the time over to him.
All right. Well, thank you, Travis. I appreciate that. Appreciate your introduction, and I also appreciate this opportunity from DSIAC to present today. Hoping everybody can hear me. Just one issue. I've just discovered how to advance the slides again. Sorry about that. Let's move forward. I'm excited to talk to you all today about my favorite topic in the whole world, spray drying. And I also want to let you know we're going to be covering a very wide variety of material today, and so I'm going to have to go very fast, especially with some of the first slides where we're just going to go over the basics. But I do think we need to at least get started on those so that it will facilitate a deeper discussion that comes later. So let's get right into the theory. Spray drying, which you probably already know, is a rapid evaporation technology, and it's designed specifically to produce powders. It does this in a very economic and efficient way, and the reason for that is because of basically how it facilitates rapid evaporation. The first thing it does is it leverages atomization, which is kind of a goofy word that just means taking the liquid that needs to be evaporated and converting it into a very fine mist with very small particle sizes. Just to give you an idea of how small these particles can be, if you imagine taking a cubic meter of liquid and spreading it over 16 acres, that's the type of surface area advantage that we get with an effective atomizer. This mist is then introduced into a heat transfer chamber where there's hot air that through convective heat transfer will evaporate the moisture. Now this, at the same time, this hot drying air or drying gas, since it's a heat transfer step, the temperature of that gas will be reduced and the saturation level of that gas will be increased. This basically spends it, so to speak. So what I mean by that is that it has to be replaced with new gas that is not saturated and is at a higher temperature. So the fourth important step in spray drying is that you need to have a mass transfer of this moist drying gas out of the chamber and replace with new gas. Now, everything that we've talked about so far is the easy part of spray drying, and it works every time. But what doesn't always work is now you have to collect these particles, which are dispersed in a stream of moist and slightly cooled gas. This is accomplished via filters and cyclones and scrubbers, or a number of different types of technology. But this really does constitute the challenge in spray drying, and most of the development work is focused on this step, making sure that the powder conveys properly through the system and can be recovered. Here's just a basic process flow diagram. This is a short form tower spray dryer and shows the basic components. Hoping you can see my mouse cursor, but basically we have a tower, and in the top I've depicted a two fluid atomizing nozzle. So compressed air is used as the energy source to atomize this liquid. The liquids start in these feed tanks and they're pumped up to the atomizer, where they're impinged violently by this compressed air. That's what causes the atomization. Simultaneously, we have fresh air being pulled through an air heater with a blower, and this air will gather the moisture and the particles and exit the chamber, usually through the side of the bottom cone. Now, this stream coming from the chamber into the next unit, which is the cyclone, this is the stream of gas that's saturated, slightly cooled, and full of powder. So it goes next into the cyclone, where centrifugal force is used to throw the powder against the walls, and then gravity pulls it down where it can be collected while the air or the drying gas goes out the top. Next, it will go through a filter house with either a cartridge or a bag filter, and this will remove the fines that the cyclone is not capable of removing. And after that, sometimes there will be a wet scrubber, and sometimes not. But the goal is, once this gas exits the blower at the end, it's clean and can basically it's clean and safe enough that it can basically be exhausted into the atmosphere. Now, there's 3 collection points shown in this diagram. There's double butterfly valves underneath the chamber, the cyclone, and the baghouse. This is because when done this way, you can actually collect different fractions of powders from these 3 steps, and the physical properties of those powders will be different. Your largest particles will come out underneath the chamber, medium particles will come out underneath the cyclone, and the fines will come out underneath the baghouse. Typically, we use a pneumatic conveying system to push the powders through this into one collection point at the very end of the system. Now, this is a diagram, or that previous one was a diagram for what's called an open single pass system, meaning the air just comes from the outside environment, passes through once, and then gets exhausted into the environment. That works when you're evaporating water, but if you're evaporating a solvent, a flammable solvent, it's not safe to do it that way. We need to first inert the system. So they create closed loop spray dryers. And how they work is there's a nitrogen supply that gets introduced into the system and circulated until the oxygen content is near 0. And this creates a combustion-free environment. And then everything else is basically the same, except that we also now have a solvent. As we're exiting the baghouse, this solvent needs to be recovered so that we can reuse the gas, since the gas is now saturated with solvent. So we put a condenser in line, and this will cool the gas and collect solvent underneath. Since we've cooled it, we now need to preheat it before we can use it again. So there's a second heater, a preheater, and then on the inlet side of the blower, and on the exhaust side of the blower, there's a second heater that brings it back up to the drying temperature. So with all of this heating and cooling and reheating, plus the consumption of nitrogen in the first place, you can imagine closed loop spray drying is significantly more expensive than single pass. So this technique is typically used for materials that can that are very high value materials. Let's see, let's move on here. Now, there's a lot of different variations in spray dryers. The ones I've just showed you are basically short form tower dryers with 2-fluid atomization, but there are so many different varieties that sometimes it's hard to even recognize a spray dryer when you see one. There's tall form towers that are much skinnier and taller. There's box-shaped spray dryers with a trough bottom, and they use a screw conveyor to convey the powders out of the system. There's cylindrical towers with a flat bottom and a vacuum arm that sweeps around the bottom and vacuums up the powders. Also, the airflow configuration can be introduced into the dryer in the opposite direction as the liquid. This is called a countercurrent dryer. There's various methods of atomizing the liquid, the most popular one being the rotary atomizer. On the lab scale, you see a bunch of 2-fluid nozzles being used, but there's also high pressure ultrasonic nozzles, electrostatic nozzles, and actually this slide doesn't show it, but there's another one called pulse combustion atomization that was invented here in the US. And then finally, the different conveying methods. There's so many different variations of a spray dryer once you consider all of these that it kind of reminds me of a pickup truck. Once you've decided, you know, the cabin size, the motor size, the bed size, etc. It's not likely that you're going to run into 2 people driving the exact same pickup truck in the same day. It's kind of like that with spray drying. Now, a lot of people are concerned about spray drying when they have temperature sensitive products. And this is a valid concern, but in my research, I found that I'd say maybe 8 times out of 10, it's not as big of a concern as either I or the customers expect going in. And this is because the temperature that the material experiences is significantly lower than the temperature that the drying gas is set to at both the inlet and the outlet of the dryer. And the reason for this is basically that evaporation is not the same thing as boiling, and it's important to understand the difference here. Evaporation is something that happens only on the surface of a liquid, whereas boiling happens uniformly throughout the mass. This is why it's very important for us to create a high surface area. Evaporation happens when the air above and around the liquid is at any temperature above the wet bulb temperature. Right, and the wet bulb temperature is something that we're not going to go into technically, but basically it's similar to dew point. It's a parameter that is affected by the saturation level of the air. Whereas boiling will happen when the liquid is at the boiling point. And the boiling point, we know, is something that's affected by the pressure of the system. What this all means is that the rate of evaporation is mostly dependent on the conditions of the air around the liquid, whereas boiling is mostly dependent on the temperature of the liquid itself. So even though we're able to evaporate stuff at room temperature, that doesn't mean we're going to operate the spray dryer at room temperature. We can actually still get away with operating the spray dryer at very high temperatures, which will increase the evaporation rate. And this is because of the way heat is transferred in a spray dryer. This is kind of a mental exercise. This is not any data that I've collected in the lab or anything. This is just an exercise to think about. But if you were to somehow able to take a parcel of air and follow it through the spray dryer and measure its temperature along the way, and then also do the same thing with a single droplet that gets spray dried in this chamber, the temperature curves might look something like this. There's basically three phases to consider. The first phase is a sensible heating phase, where that energy transfer is used basically to, or primarily to increase the temperature of the droplets. And evaporation is occurring here, but it's occurring slowly. And the rate at which it occurs is increasing as the temperature of that droplet approaches the wet bulb temperature. Once the droplet hits the wet bulb temperature, you enter into a second phase of heat transfer, where it's a latent heat transfer step, meaning the energy transferred is used primarily to facilitate a phase change, and there isn't much temperature change for the droplet, even though the air temperature will be decreasing. This is because you're spending energy on the phase change as opposed to a sensible heating or a temperature change for the droplet. And during this phase, the evaporation rate will be constant, and it will be limited by the surface area of the droplets. But eventually we run out of moisture, or the moisture level gets very low, and we start to form a crust. These droplets are turning into particles, basically. So there is a crust of solid material on the outside. There's still moisture in the middle that may have already transitioned into the gas phase, but it's stuck, and it has to diffuse through this layer, through this crust. This causes the evaporation rate to fall, and it causes the particle to enter into a second sensible heating step. If you're able to run the spray dryer with parameters such that most of the material is exiting the spray dryer shortly after this second sensible heating step begins, then it's possible to keep the temperature of the powder easily below 40 degrees Celsius throughout this whole process, even though you may have an inlet temperature of 250. Although some materials will not dry properly in this last step unless you do give it adequate time in the sensible heating step. So it kind of depends on the physical properties of this crust that's formed, and different materials will do that differently. But it is entirely possible with certain materials to accomplish this below 40 degrees Celsius. General rule of thumb: typically the material at the outlet will be at least 20 degrees below the outlet temperature of the air. So let's look at the characteristics of a spray dried particle. I've got two SEM images here. The one on the left is a particle that dried pretty well. There's a few problems, but the first thing I want to point out is notice that it's a hollow sphere. This is because of that crust formation that I was telling you about. You can see holes in the top and on the bottom, and you can also see these bulges. This happens during that diffusion limited step, where the evaporated moisture has to escape this solid matrix one way or another. There's also a bunch of little pinholes that you can see. So sometimes that moisture bursts through and it creates a blowhole, and sometimes it starts to blow bubbles on the surface. This is a material that must have gone through an elastic state, as it must have been warmed enough that it had some elasticity, and the escaping gases could form bubbles like this. Now on the right, we've got particles that were over dried. And you can see a lot of issues with these. There's what I call a shriveled pea in the top. It looks like a canned pea that got microwaved for too long. And then you see a bunch of shards, basically. These are hollow spheres that blew apart. And so you'll also see some like partial hollow spheres with smaller hollow spheres within them. Very interesting things that you'll see with the SEM when you look at these. But the main consequence, I guess, that I want to point out with this is, the main drawback of spray drying is that oftentimes the powders that they produce are so light in terms of density that it will result in poor flow characteristics. And also sometimes they'd be very hard to reconstitute back into a liquid. This is because The particles are so light that they can't even break the surface tension of water. We'll talk more about this later. I want to jump straight now into development and scale up because I decided I think this is probably what most people are here to learn about. There's two methods in which an organization can scale up spray drying. One is where they take on all roles themselves. In other words, they're going to be their own manufacturer. They're going to design a production plant, build a plant, and run their own spray dryer. And before they do that, they will have to do some process development, which means they're designing and building a pilot plant as well. I'm not saying this is the wrong way to do it. There are many situations where this is the right way to do it, but more often than not, the cheaper and faster way to do it is more of a coalition model where you leverage external manufacturing and external process development. This saves money because you don't have to buy equipment, but more importantly, it saves time because you can leverage the fact that there are places set up already with the equipment that you need and the skill and the staff, and you know, you can basically show up and hit the ground running. But there still is, it's still required that somebody acts as a program manager throughout this entire process till the day you're done manufacturing, basically. Somebody from usually within the originating company or the organization that developed the technology will be the program manager. And again, I'm assuming that many of you here listening to this will be that person or at least on that person's team. So I want to go over in the next couple of slides ways to help you streamline the scale up process from that role. Here. So I want to talk about a thing that I call product intuition. This is basically the key ingredient to a very good scale up. And product intuition is something that basically only the inventor or the originator of the technology has. They have this intuition from handling their materials in the lab for the last 5 years and from talking to their customers and just understanding what the market wants, what it needs, and what it will tolerate. These are things like properties of the feed material, the behaviors of the feed material, challenges that will be faced during scale up, the desired properties of the product, and the tolerance within the market for changes in these properties. So we'll go into each of these in detail. Let's start with the properties of the feed material. These are things like the physical form. For example, is it a solution or is it a slurry? That will have effects on how it is processed. What's the solid content in the feed material? Typically, the higher the content, the better. A 50% solids solution will be cheaper to dry than a 5% solid. What are the rheology characteristics of it? Viscosity will change across temperatures, but it's something you should measure. Will this be pumpable from a tanker truck when it's 10 below zero in Minnesota in the winter? You know, how does the viscosity change across shear rates? This is important because all atomization methods introduce high shear. If you've got a non-Newtonian fluid, this might prohibit it from being spray dried. The density is important when we're talking about shipping and storage, and obviously the pH can be important. Some materials will spray dry better at a higher pH than at a lower pH. So do you have flexibility in your material to change the pH? Let's talk about the behaviors of the feed material. Is it something that needs to be kept warm before you spray dry it? Do you need high shear agitation to keep it as a homogeneous mixture before it's pumped into the spray dryer? Are there any pumpability issues beyond viscosity changes that we should consider? And what is the shelf life? Do you need to have this spray dried immediately once it's arrived on site, or can it be stored? And if it can be stored, do you have special storage needs? Does it need to go into an agitated silo, a temperature controlled silo? Can it be stored in drums? Do the drums need to be in a hot box? Can they, will it freeze if it's left in a cold warehouse? Things like that. You also need to look at materials compatibility. If you've got a material that corrodes metals, then you need to talk to the folks you're working with and make sure they have the proper materials of construction for every wetted piece of equipment in the process. And also, what upstream processing needs do you have? Does it need to be homogenized? Is there blending? Is there a brewing step or an extraction? Anything that requires equipment beyond a basic mixing tank, that's something important to think about and identify as early as possible. There's a good chance you may have to provide that equipment. What challenges will you likely face during scale up? These are things like reactions. What does the material react with? Do we have to keep it segregated from certain things? Are there handling issues? A lot of people will be exposed to this. We want to keep them safe. What about licensing and waste concerns? This can be anything from certifications, like quality certifications that you're looking for, like GMP, food grade, kosher, pharmaceutical grade, organic, all the way to like environmental exposure licenses. If there's something, a toxic gas that you're going to be releasing somehow at the end, you need to get licensing and permitting for that. What will the effluent gas smell like? A lot of products, the gas coming out will have an odor that maybe the local people living in the city or town where you're processing, they don't want to smell this. So you may have to introduce a scrubbing system or an odor reduction. Are there packaging concerns? The cost will be greatly affected by whether, if you're just going to package in a super sack, for example, that will be much cheaper than if you need to put your powders in a stick pack, and then the stick packs go in a box, and the box goes in a case, and then the cases get stacked on a pallet, wrapped, labeled, and shipped, right? That's going to cost a lot more, and you got to make sure that the facility is equipped with the packaging line to do that. Housekeeping issues, this mostly gets back to your quality programs. But most importantly, there's the things that the chemists notice in the lab. This is a special type of intuition that you really need to pay attention to. This is when, they complain that, oh, the glassware is sticky. It's very hard to clean the glassware after I've handled this. Well, it's going to be very hard to clean the spray dryer too. There's a lot of valuable information that you can get by paying attention to those things. Obviously, this is a joke. I've never met a chemist who complains about anything. Let's see here. The desired properties of the product. It's very important to identify this as soon as possible as well. Bulk density is important if you're going to be blending this with other powders downstream. You want the density and the particle size distribution to match as closely as possible so that you don't get segregation of powders in a blending or conveying step or packaging step downstream. What moisture content do you need to hit in order to maintain the shelf life? Is this going to be redispersed in water? If so, you're going to need a dispersible instantized powder. Are you targeting a color? Spray drying can affect the color in some cases. Do you need good flowability? If there's complicated packaging or downstream processing, a lot of times flowability of powders will be a big issue. And you would address this by looking at cohesion, hygroscopicity, and caking. And finally, are there any downstream processing needs? Just like the upstream processing needs, if there are needs, you may have to provide that equipment yourself. And then this is the most important one, in my opinion. This is the market tolerance issue. So it's kind of like when you go to buy your first home and you have a wish list, but you just can't afford to get everything on there. Something's got to give. Well, the only person who can make an educated and informed decision about what things can be changed is somebody from that originating company who understands the market really, really well. And one of the things that I can at least help you with now to help make those decisions is we can talk about cost variables, the most important cost variables in spray drying. And these are formulation costs and conversion cost variables. Now with formulation costs, the things that are going to be most expensive are things like clean labeling, nutritional value, and raw material sourcing. So if you're making a food product, for example, and you don't want any modified food starch in there, That's actually going to add quite a bit of cost to the process because modified food starch is cheap and it works really well. And so you will likely be replacing it with something that is expensive and doesn't work as well. But you'll get that clean labeling, and that may allow you to sell your product at a higher price point. It will also affect your raw material sourcing. It's very important to make sure you have multiple sources for every single raw material. I've got a lot of customers right now who can't source anything because of the supply chain issues that are happening across the world. Now, when it comes to conversion cost, these are in order, in my opinion. The main variable that will affect the conversion cost is the percent solids in your feed material. Remember, we're paying per pound of water evaporated, not per pound of powder produced. So if you've got a 50% solution going in, it will be 10 times cheaper than if you have a 5% solution going in. It'll be cheaper on a cost per pound basis. The second most important variable is the temperatures used. The larger your delta T between the inlet and the outlet temperature on the spray dryer, the higher your evaporation rate, and therefore the cheaper the process will be. The third one is the campaign size. So if you show up to a toll manufacturer with 2 50-gallon drums to spray dry, it's going to be a lot more expensive than if you're showing up with 2 tanker trucks every day for 20 days in a row. They like to run continually and for as long as possible. It really helps the economics. Less important are the ancillary equipment needs that we've already talked about: upstream, downstream processing, and complicated packaging. Okay, so I wanted also to kind of go into advanced spray drying techniques. A lot of people think that spray drying is just a blunt tool that is used for making, powdered milk, for example, which is actually a very complicated process. But there's a lot of high-tech science involved in spray drying, and there's a lot of very cool things that can be done that most people don't know about. Unfortunately, I think we've only got about 10 minutes to go over these, so I'm going to breeze through them at a high level. But yeah, let's get started. The first one is altering the glass transition temperature. This is a glass transition is when you create a powder in the drying chamber, but it hits the walls, and upon contacting the hot surfaces, it transitions into this rubbery, sticky film. And instead of collecting powder at the spray dryer, you get no yield whatsoever because you're just coating the whole spray dryer with something that looks like hard candy. There's 2 ways to fix this. One is to spray dry at a lower temperature, but that's expensive. The second way is to alter the glass transition temperature of the material you're trying to dry, and this is accomplished by mixing the material with high molecular weight molecules such as proteins or polysaccharides. This increases the glass transition temperature and allows you to operate the spray dryer at a higher temperature and still obtain a free-flowing powder. The downside is you've diluted your material with a protein or a polysaccharide. The second one, I'd love to spend a lot more time on this slide, but unfortunately I can't. This is surface modification. If you look back at this picture here, this is a particle that has gone through a surface modification step where it looks like the surface has been peppered with something else. If you saw that image, you may think, oh, we created a particle and then we sprayed it with something else because it looks like that. But actually how that happens is you can mix materials together before spray drying, and because of the way droplets, because of some pretty interesting mass transfer characteristics that occur when you're evaporating, a droplet over the course of 300 milliseconds. Solids within that will migrate to the surface, and they form this hollow shell, but they will migrate to the surface at a different rate. And those different rates are categorized by the different chemical and physical properties of the material. So you can actually build layers in this way. You can get certain molecules to migrate to the surface faster than other molecules. and create layered particles. This next one is a very popular technique right now, oil encapsulation or microencapsulation, they call it. And this is where if you want to create a powder out of an oil, you can imagine, I mean, that's an impossible thing to do. Oils are not solids at room temperature by definition of what they are. And there's no amount of, removing water that will magically turn it into a powder. I tell my customers, yeah, you can't just dry an oil and create a powder, because the problem was never that the oil was wet in the first place, right? It's a liquid, but it's not one that will be evaporated in a spray dryer. So anyway, but what you can do is you can entrap droplets of oil in a casing of some sort of solid water soluble powder. These are things like maltodextrins, pectins, alginates, gums, for example. And this creates a shell with a bunch of little droplets of oil inside. And the basic step is to create an emulsion first and then mix it with these wall materials. This works because wall materials are good film formers. They dehydrate very quickly, and this forms that diffusion layer that we've talked about, and the oil must diffuse through the film, and this entraps the oil inside the matrix of wall material. This is known as matrix encapsulation, because instead of having one droplet surrounded by a shell, you have a whole bunch of droplets embedded within a matrix. This next one is, I actually don't have a lot of experience in this, so I've chosen instead just to reference some folks who do have a lot of experience. But spray dryers can be used to create powders with viable probiotics and microbes and viruses. Meaning, what I mean by viable is that you rehydrate this powder, and these microbes are living. They're viable and alive. Despite the high heat used. There's a number of ways to do this, but basically you have to protect the probiotics from the shear of the atomizer, and you have to stabilize them during this gel fluid phase transition that happens that can rupture the lipid bilayers. And also microencapsulation is part of this. Usually you have some sort of vitrification or thermal protectant agent that is included in the formulation and can protect them from the heat of the spray dryer as they're traveling through. Again, microencapsulation can be used to create flavors and, to create powders out of flavors and volatile materials. If you think about it, this is kind of weird, because a volatile material is something that has a very high vapor pressure. That's why we can smell it. So you can imagine in any evaporative process, those are going to evaporate quicker than water. So this is why, typically if you spray dry coffee, it doesn't taste as good as coffee that has been freeze dried, for example. But lately there have been advances in technology, not only in the construction of the spray dryer, but also in formulation techniques that allow flavors and volatiles to be encapsulated and preserved in spray drying. Long story short, it comes down to something known as selective diffusion that happens during the drying step. There's also flavor masking. Now, if you've got a material that tastes terrible, like a pharmaceutical or something, but you want people to, want to be delivered as an oral powder, there's three basic strategies. You can cover the flavor with a stronger flavor. You can block the receptors, the taste receptors on the tongue with interference molecules. But what works the best is you can cloak these flavored molecules with cyclodextrins. And cyclodextrin is just a dextrin that is cyclical, and it creates I forget this shape, a frustrum, I think is the shape of it. It's like a three-dimensional cross section of a cone. But anyway, you can actually fit certain molecules inside of it. And so when the particle contacts the tongue, the cyclodextrin is blocking the receptors as the active ingredient gets absorbed. And then finally, there's nanoparticles. This is fairly new. and it requires special equipment, both with the atomizer and the collection of the powders. If you remember one of the first slides, I was talking about how cyclones, they don't do a good job at capturing fine particles. This is typically anything smaller than 1 micron, you don't get good recovery in a cyclone. So if you're targeting 300 nanometers, for example, you're going to have to use either a filter, a HEPA filter, or an electrostatic precipitator to collect those particles. And you know, the filters actually don't work so good either, because it's hard to then recover. You can trap the particles on the filter, but then to recover those particles into a collection source is actually, that doesn't work so good with nanoparticles. Although electrostatic precipitators thus far have been pretty difficult to scale up. So you typically only see nano spray dryers on labs as a lab scale device. Basically, with an electrostatic precipitator, you have to open it up and scrape the powder off of the electrodes using a rubber spatula. So it's a very manual process. And finally, I told you previously about some particles, they don't flow well, spray dried particles, because their density is so low that they can't break surface tension. And they also won't dissolve very well. This is fixed through various processes known as instantization, which basically means we're making an instant powder. But one of the most effective methods is fluid bed agglomeration. And with fluid bed agglomeration, you take a spray-dried powder and you put it in equipment that creates a fluidized powder, meaning it's behaving like a fluid. The particles are dispersed discretely in this moving stream of air so that they're behaving somewhat like a fluid. And we're using warm air for that, and then we can spray a binder from below using a 2-fluid nozzle usually. The binder in many cases can just be water, but sometimes it's water with a salt or water with like a polyvinyl alcohol or something like that. What this does is it creates water bridges between particles, which because of the hot air, they evaporate and shrink. This pulls the particles together and they become fused. There's a small amount of dissolution and then re-evaporation that happens that kind of welds the particles together, and you get an agglomerate. It's not any denser than a spray dried particle because it still consists of hollow voids, but it has an irregular shape. And when you put a slug of this in like a glass of water, for example, there's cracks and void spaces that water can diffuse through. So it's actually breaking the surface tension, even though the density really hasn't changed. It's more the shape that causes this to happen. On the right here, I have an image of spray dried particles that have been agglomerated. Okay, I think we just barely made it. It looks like I'm 1 minute ahead of schedule. Hopefully we still have time for questions, if we have some, Travis.
Yes, I'd just like to, remind people that if they have questions, they can put it in the question area or within the chat, and I can get them up there. So far, thank you very much, Steve, for that. While we don't have too many of them right now, I do have one that I myself had, and that is how prevalent is spray drying and producing powdered material for additive manufacturing applications? It would seem that it could be beneficial for flow issues of the feed material.
That's a very good question, and it's one that I've been looking into myself. Spray drying is not, how do I put this? It's not necessary in additive manufacturing. So in other words, you can create metal particles for additive manufacturing through processes other than spray drying. But it is an interesting opportunity, in my opinion, because it would be interesting to produce these raw materials via spray drying, because it gives you opportunities to, for one thing, you can make very homogeneous blends of metals, much more homogeneous than you can get by blending, let's say, like metal nanoparticles together in a ribbon blender, for example. It would be much more homogeneous just to create a slurry of these metal particles and then spray dry them. But if you're actually able to dissolve the metal in a solvent and reprecipitate it in a spray dryer rather than having it pass through the spray dryer as a spectator, you know, in a slurry, then you can actually change the physical structure of the metals and create these very lightweight and very porous particles that I'm currently investigating if that would be something that would be of interest or of benefit to you know, 3D printing or cold spray repair, for example. I think that there's still a lot of unknowns about this, but in my opinion, there's a whole bunch of, there really is a lot of potential for spray drying to be used in additive manufacturing.
Thank you. The moment we do not have any other questions, so I will wait for a couple minutes to see if any come in. In the meantime, I'd like to just say that if you have any questions outside of this presentation, feel free to contact DSIAC through our website, create an inquiry, and we can get you in touch with Steve, or if he wants to throw his email in the chat to get in further touch, whichever works easiest for everyone. And a reminder that this is being recorded and will be available in the near future. And if there's anything else you'd like to say in the meantime while we see if any other questions pop up, Steve, go ahead.
Sure. Yeah, again, it's a bummer that I had to go so quickly through a lot of the advanced technologies, but and you know, compounding that or making it even worse, I guess, is that I was not able to talk about the work that I'm doing directly for DoD right now, unfortunately, because of confidence issues. But if there are any folks that are interested in those type of applications, mostly involving manufacturing of explosives, then the way you can get more information is to contact either myself or DSIAC directly and just ask to be put in touch with me, and then we can go through an NDA process with my DoD customers. And then you would be able to speak directly with them. Much of what we're doing is not, is not top secret or anything like that, but they just wanted to keep it as non-disseminated, I guess, as possible. So that was the reason for that.
Okay. Well, still not seeing any other questions pop up. So, you know, once again, it might be that people will have them after or after rewatching. So if you do have further questions, as both Steve and I had said, you can either reach out to him directly or you can reach out to DSIAC, create a technical inquiry, whether it's directly on this topic or something related, and we can get you those types of answers. Oh, we got one question.
It looks like
Yep. Great presentation. Have you evaluated a spray drying technology that employs an ionization field? This has been commercialized by Polar Dry, a division of Fluid Air, by Andrew J. Beckel.
Yeah, thanks, Andrew. This is a great question. Yeah, Polar Dry, and there's actually one other company that has developed this technology that uses an ionization field. This is basically the electrostatic ionization method of atomization. It actually works a lot like how the ionization takes place in a mass spec, for example. It's just a scaled up version of that. And it has a lot of advantages. One of the advantages is that it does allow you to operate the dryer at much lower temperatures. Some materials like flavors and fragrances can be spray dried at 20 degrees Celsius, for example, with this ionization technology. And the reason for this is that you actually don't get hollow spheres when it's atomized this way, you get a particle with uniformly distributed density. And this eliminates that diffusion limited step that happens at the end of the drying curve. And it allows you to leverage the evaporative cooling capabilities throughout the entire life of this particle as it's being dried. So that's the first advantage. It's very good for flavors and fragrances, anything that you want to, where you want to maintain, like with coffee, for example. But it's also good with probiotics, anything where you need to maintain viability. There's less shear with the atomization method than there are with all of the others. And then finally, another advantage is that you can actually get enlarged particles with this technique. There's a way that you can actually pulse the ionization field, which causes the particles to agglomerate because they're charged. These particles are charged and attracted to one another. So you can actually cause the particles to agglomerate before they exit the chamber. Thus far, you know, if you want to agglomerate a spray dried particle, you have two options. You can do it in a post-processing step, so spray drying followed by an external fluid bed, or you can buy a very expensive integrated fluid bed dryer. And as of the last, I'd say it's probably only been about 10 years, you have this option as well. So yeah, it's very interesting. It's exciting technology. It's still a little young, but from what I've been able to keep track of, they're making very good traction very quickly and are making some very good powders through this process.
Great, thank you. Not seeing any others. So if there aren't any other questions, I would like to thank both you, Steve, for the great presentation, and to all those who have attended. And we look forward to any further questions and hope to see many of you at our next webinar. So thank you again, Steve, and it's been very informative.
Thank you, everybody. Appreciate it.